Hi, in this video we're going to look at how we can get an exponential function for a word problem, just given some verbal information about the situation that we're modeling. So in word problems, exponential functions are generally called exponential growth functions or exponential decay functions. They're growth functions if the amount that we're talking about is increasing as time progresses, and it's called a decay function if the quantity is decreasing as time progresses. We already saw a few examples where we were given the function, so let's kind of recap what we already saw. So we saw this function, n of t, and it modeled the number of Netflix subscriptions t years after 2007. So n of t was 5,723 times 1.33 raised to the t, and this was in thousands of subscriptions. And t was supposed to be years after the year 2007. And we saw that t equals 0 corresponds to 0 years after 2007. So if we wanted to know the number of subscriptions at the beginning of the year 2007, all we had to do was plug in 0 into that function n. So n of 0 is 5,723 times 1.33 to the 0, and that was thousands. And 1.33 to the 0 is just 1. So we get 5,723 times 1,000, which is really 5,723,000 subscriptions. So we saw that to get the initial amount, we just had to plug in t equals 0. And similarly, we looked at a function that gave us a future price of some item, and we were told that we used the rate of inflation of 3.7% a year, and the function looked like this: 1,500 times 1.037 raised to the t. And if we wanted to know the current price of the item, we would just plug in, again, just t equals 0, because the current price means it's 0 years from today. So plugging in t equals 0 to get the current price, we get p of 0 equals 1,500 times 1.037 to the 0, and again, we just get that number, 1,500. So the current price of the item is $1,500. So we're sort of learning how to get a function if we know some information about the quantity that we're describing. So let's kind of summarize what we've seen so far. So if we're looking for an exponential growth or decay function y of t, we know it's going to look like this: some number a times some other number b raised to the t. We also know that that number a is really going to be the initial quantity, or the initial value, y of 0. So that's important. We could use that information when we're building functions. So let's look at another example. So in this example, so this isn't on that worksheet, it says there was a sample of 750 milligrams of a radioactive substance to start a study. Since then, the sample has decayed by 9.7% each year. So let's try to write down a function that describes the quantity of, or the amount of, this radioactive substance at time t. And here we're going to use t is in years because it says each year. So first of all, we see the initial value right there. We're starting with a sample of 750 milligrams, so we know the initial quantity, y of 0, is going to be 750. So we can say the function is going to look like this. Y of t is equal to 750 times something raised to the t. So now all we have to fill in is that something. What is that amount that we're going to raise to the t? So let's look back at the statement, the description, and there's another number we haven't used yet. That's 9.7. 9.7%. So you might think, well, let's just put 9.7 in there. And so maybe the quantity is 750 times 9.7 raised to the t. But if you test it out, let's say after 1 year, t equals 1, how much of the substance would you have? So 9.7 to the 1 is 9.7. It's more than 9, a little bit less than 10. So you would be multiplying 750 by something between 9 and 10, so you'd be getting a pretty big number. And that would be an increase, not a decrease, in that the quantity of that radioactive substance. That's not quite what's going on here. So that's because we're told that the sample is decaying, the quantity should be decreasing. So let's go back to the drawing board. We're decreasing by an amount of 9.7% each year. So let's look for a pattern and see if we can figure out what that number is that we're going to put in there. So we said that when t is equal to 0, so no time has passed, we're starting with 750 milligrams. So we know y of 0 is 750. So how much are we going to have a year later? So when t is equal to 1, y of 1 is going to be the amount we had previously, so the amount we started with, which was 750, minus 9.7% of that amount, right? We're losing 9.7% each year. So we're going to subtract 750 times 0.097. So 9.7%, we have to move the decimal place to the left 2 places, so we get 0.097. So we're subtracting 9.7% of the initial value. Now we're looking for a pattern, so we're not actually just going to put all this into our calculator and get an amount. We want to look for a pattern, so we're going to kind of simplify it. So what I'm going to do is, I notice I have 2 terms, and they each have a 750 in them. So I'm going to factor that out of each of those terms. It's the GCF, right? So I'm going to factor out a 750, and then what am I left with? In the first term, if I factor out a 750 from 750, I'm left with 1. And then in the second term, I'm left with the 0.097. So now I can do the subtraction 1 minus 0.097, and I get 750 times 0.903. So I'm going to leave it like that because I'm looking for a pattern. I don't want to multiply those 2 things together. Now let's go 1 year later. So when t equals 2, how much of the substance do we have? Well, we've decreased it by another 9.7% from the previous year. So y of 2 is going to be the previous year's amount, 750 times 0.903, minus 9.7% of that amount. Okay, so you take the previous year's amount and then you subtract off the previous year's amount times 9.7% or 0.097. Now, I'm looking for a pattern. I want to simplify this a little bit. I don't want to actually put it in my calculator and get a decimal. But notice again, we have two terms. We have a term minus another term, and each one of those has a 750 times 0.903. So that's a GCF I can factor out. So I'm going to factor out that whole thing. And what am I left with? I'm left with a 1 in the first term and a 0.097 in the second term. And now 1 minus 0.097, I saw before, that's just the number 0.903. So I just simplified the 1 minus 0.097. And now notice I have 750 times 0.903 times another 0.903. So I can write that as 750 times 0.903 squared. And now I look back and I say, do I have a pattern? So when t was equal to 0, we had y of 0 equals 750, just 750. But I could write that as 750 times 0.903 to the 0. Okay, because that's just 1. Anything raised to the 0 is 1. And then we see that when t is equal to 1, y of 1 was 750 times 0.903 to the 1. And we see that when t is 2, y of 2 is 750 times 0.903 to the 2. So we clearly have a pattern, and it looks like the base, the number that's being raised to a different power every year, that number is 0.903. And so we go back to the equation up above. We're trying to find an equation for y of t, and we have 750 times question mark, and I can replace that question mark with a 0.903. So the function that models the quantity of that radioactive substance is just y of t equals 750, the initial amount, times 0.903 to the t. Okay, so let's kind of put it all together and describe what we just figured out. So we call the rate at which a quantity, a substance grows or decays, we call that the decay rate or the growth rate of the substance. So we're going to call it R. So we have a growth rate or a decay rate in each word problem. Call that number R. So first of all, if the quantity y of t is growing exponentially at a rate R, then we can write down the quantity y of t is equal to the initial amount, y of 0, times 1 plus r raised to the t. So we saw in the last example it was 1 plus 0.097. No, the last problem was a subtraction. That was a decay problem. Sorry. So if the quantity y of t decays exponentially at a rate r, then we can write down y of t is going to be the initial amount times 1 minus r raised to the t. Sorry, there's not a t there. There should be a t. There we go. So the growth rate, we just add it to 1. If it's a decay rate, we subtract it from 1. And now we know how to build the function from just the information given to us. So let's look at the last example on that worksheet. So this is the one we didn't get to in class. So number 7 says, assume that the size of the rat population at Fisherman's Wharf, that's in San Francisco, grows at a rate of 8% monthly. If there are currently 200 rats at Fisherman's Wharf, I'm sure that's not how many rats there are. I think there's probably thousands. But assume there's only 200 rats at Fisherman's Wharf. Find an exponential function that models the rat population t months from now. So this is clearly a growth function, and we clearly have 200 current or initial rats. So P of 0 is the initial value, and the growth rate is 8%. So we're just going to write down the function given all that information. So 8% is 0.08. So we can write down P of t is equal to the initial population, 200, times 1 plus that growth rate, 1 plus 0.08 raised to the t. And I can simplify it just a little bit and call it 200 times 1.08 to the t. So then we can use that in part B. So in part B it says use your function to predict the rat population at Fisherman's Wharf in 2 years. So we have to remember that our function models the rat population t months from now. So 2 years from now, t is 24 months. So we're going to plug in 24 into our function. P of 24, the population 24 months from now, is 200 times 1.08 to the 24. And now remember, when you're using your calculator, you're going to put in 1.08 and then use the y to the x button and hit y to the x and then 24 and then equals, and you get a long decimal. Now leave that decimal, leave that number in your calculator, don't write it down, and then just hit times and then 200. And then you'll get another decimal, but you're going to round it before you write it down. So how are you going to round it when the problem doesn't tell you what to round it to? It doesn't tell you how many decimal places to use. Well, you have to remember, you're talking about rats, right? The population, the rat population means how many rats you have. So does it make sense to have 2/10 of a rat? I would hope not. So let's round it to the nearest whole rat. So if you round it to the nearest whole rat, you should get 1,268. So we should have about 1,268 rats in 2 years. That's a lot of rats. We started with 200, and in 2 years that grew to over 1,000. All right, so now we know how to build a exponential function, either a growth function or decay function, from a word problem that just gives us information. We need the initial quantity, the initial number of things, or the initial amount, and then we need the growth rate or the decay rate. If it's a growth rate, we add it to 1. If it's a decay rate, we subtract it from 1. All right, so lesson 21 on Alex is due on Friday night? No, Monday night. Good luck.